Welcome to The Explainer. Today we're diving into one of the biggest questions in all of science. What gives matter its mass? What gives stuff its actual stuffness? The answer is tied to a particle so important, and for a long time so mysterious, that some people even nicknamed it the God particle, the Higgs boson. So let's just take a look at this. It looks like, well, beautiful chaos, right? A firework display at the smallest possible scale. But what you're seeing is a real snapshot from a particle collision. And hidden inside patterns just like this one, scientists finally found the answer to that huge question that had been bugging them for half a century. Why do things have mass at all? To really get why this was such a huge deal, we've got to look at our best blueprint for the universe, which is called the Standard Model. And for decades, this model was pretty much perfect, except for this one glaring fundamental flaw that just didn't make any sense. Think of the Standard Model as the universe's rulebook. It tells us what all the basic building blocks are and how they're allowed to talk to each other. And for years, it was unbelievably successful. Seriously, almost every experiment we could dream up just kept proving it right, again and again. But here's the giant problem. The deep mathematics of the theory, the very foundation it's built on, demanded that some of the most important particles, the ones that carry fundamental forces, had to have zero mass. They had to be weightless. But when we went out and found them in experiments, they were massive. Incredibly heavy. So you have a complete contradiction. The rulebook said one thing and reality was doing the exact opposite. So what do? How do you fix that without just tearing up your most successful theory ever? Well, the answer turned out to be adding a completely new and kind of weird ingredient to the entire universe. The idea, which first popped up way back in the 1960s from physicists like Peter Higgs, was totally out of left field. They took a basic assumption we all have about the universe and just flipped it on its head. They asked, what if the vacuum of empty space isn't actually empty at all? They suggested that space itself is filled with an invisible, universe-wide energy field. It's just everywhere, all the time. And here's where it gets really mind-bending. The field isn't in space, like air in a room. The field is a property of space itself. So every single point in the universe, whether it's in the heart of a star or in the deepest, darkest void, is soaked in this Higgs field. Okay, the best way to picture this is to imagine the entire universe is filled with invisible, cosmic syrup. As particles try to move through it, some of them feel a resistance, a kind of drag. And it's that interaction, that drag from the field, that we actually perceive as mass. So how does that actually work? How does this field give mass to some particles but leave others totally untouched? Well, let's rewind to just after the Big Bang. The universe was this incredibly hot, chaotic soup. And back then, the Higgs field was essentially off. Everything was massless, zipping around freely. But as the universe expanded and cooled, it hit a critical temperature and went through a phase change, kind of like steam condensing into water. The Higgs field suddenly turned on everywhere at once. And in that instant, everything changed. And here's the really elegant part. A particle's mass isn't random. It just depends on how much it feels this field. So very heavy particles like those W and Z bosons, they interact a lot with the field. They get bogged down, and that's why they're so massive. But then you have a particle like the photon, a particle of light. It doesn't interact with the field at all. It just zips right through without feeling any drag, and that's why it has zero mass and travels at the speed of light. This is such a revolutionary idea. Just think about it. Mass isn't something a particle is just born with. It's not an intrinsic property. It's something that happens to a particle because of its interaction with this invisible field that fills all of space. So for almost 50 years, this was just a really beautiful theory. It solved the problem perfectly, but it was totally unproven. Come on, how could you possibly detect an invisible field that's literally everywhere? Yeah, that was the multi-billion-dollar question. Luckily, the theory gave us a clue. It made one very specific, very concrete prediction that we could actually go out and test. The theory said that if you could dump a huge amount of energy into one tiny point in the field, you could essentially flick it. You could create a ripple, a tiny excitation of the field itself, and that ripple would manifest as a particle, the Higgs boson. Finding that particle would be the smoking gun. Now, making a ripple like that takes an unbelievable amount of energy. And that's exactly why humanity built the Large Hadron Collider. It is quite literally a machine designed to smash protons together so violently that for a fraction of a second, we create conditions not seen since the Big Bang, hopefully shaking a Higgs boson loose from the field. But there's a catch, of course. The Higgs boson is incredibly unstable. It vanishes in less than a trillionth of a second, so you can't just take a picture of it. Instead, scientists had to look for the very specific spray of other particles it would decay into. It's like trying to figure out what kind of firework just exploded by analyzing the pattern of sparks it left behind. And then, on July 4th, 2012, the entire world of physics basically held its breath. After sifting through the data from trillions of particle collisions, scientists at CERN walked up to a podium and announced to the world they'd found it. This was such a historic moment. It wasn't just about finding a new particle. It was about confirming the entire theory of how mass comes to be. It was the final missing keystone of the Standard Model. And when it clicked into place, the whole structure was finally complete. And finding it allowed us to measure something truly profound: the actual background strength of the Higgs field itself. This number you see here, it's now considered a new fundamental constant of nature, right up there with the speed of light or the strength of gravity. And what's so wild is that this one number essentially sets the rules for our whole universe. If it were even a little bit different, the masses of fundamental particles would be all wrong. Atoms could never form, stars wouldn't shine, and we definitely wouldn't be here. But you know how it goes in science. A great answer just opens the door to even bigger, weirder questions. For instance, the Higgs boson's own mass is strangely, suspiciously light, which is a big puzzle. And the energy of the Higgs field itself should, by all rights, be making the universe expand so fast it would tear itself apart. So why isn't it? So finding the Higgs boson perfectly completed the Standard Model, our greatest map of reality. But in doing so, it also acted like a giant spotlight, showing us all the parts of the map that are still completely blank. It tells us nothing about dark matter or dark energy. It leaves us with these deep puzzles about the nature of the vacuum. Finding the Higgs wasn't the end of the journey. It was really just the end of the beginning. And it leaves us all wondering, what else is out there, hiding in plain sight in empty space?